Hi, it's Anonymous, and today I really felt like talking about uh, these helicopters because, they defy conventional wisdom. So I really think that's a great subject to talk about. So, when we imagine a helicopter, we have like the path that the blades take, of course, the blades themselves, we have the mast, leads down like so, the tail boom, and of course, you can't forget your landing gear, and I guess the pilot. Okay, so this is a helicopter. Maybe you have an extra fin there. Protect the back gear, back rotor. Anyways, so say that the helicopter blade is rotating this direction. So from the top view, so it's like the side view, so it's rotating this direction. So if you look at it from the top view, it'll look something like this. All right, it'll be rotating like so. And we can see that it is actually going counterclockwise. Because clocks move from 12 to 3 to 6, but this is moving 12, 9, 6. So we see that this blade is moving counterclockwise. And using our rules of physics, this action causes angular momentum. So using the right hand rule, angular momentum will be pointing up. All right. So this is the current angular momentum of the helicopter in a hover. I'll just call it L current, LC. Now, what happens if the helicopter would like to go in the forward direction? Right, so what happens if we want the helicopter to go in the forward direction? Well, I've drawn the helicopter again, and I've drawn the angular momentum vector of what the blades would look like if they were going forward in the forward direction. Okay, so this is a vector approach. So let's redraw these vectors. So we have LC, and we have LD. All right. And then if we want to take the difference of these two vectors, then we subtract them. And this is the difference. All right. So this is the difference between LC and LD. Note that a change in angular momentum is equal to torque. Now this is your torque. All right. So what does that imply? Well, in order to generate a torque in this direction, using the right hand rule, there must be a spinning motion or something that will cause the helicopter to spin into the page. Like so. So for this reason, whenever helicopter blades move, whenever the motion of the helicopter is forward, the blades must produce a thrust in such a way that it will cause the helicopter to rotate 90 degrees before we actually see any sort of motion occur. So this effect literally means that we have a helicopter blade rotating counterclockwise, like so, and what that will do is then if we want to move forward, we'll have to impart a torque such that the blade actually will rotate like so. And that will then cause the helicopter to move forward. So we basically have to wait 90 degrees before the helicopter actually moves forward. Because if we want the desired angular momentum to be in the forward direction, and the current angular momentum is vertical, there must be some torque that's imparted on the blades, and this torque is usually caused by some sort of servo linkage arm or something like that. And that's just one fascinating take at helicopters that most people aren't aware of. Now, say that we have contra-rotating motors where one rotor is spinning counterclockwise and the other is spinning clockwise. From this, we'll be able to see that we have angular momentum going up in this direction, and then we have angular momentum going down like so. I'll call this angular momentum current top, angular momentum current bottom. And so if we want to move forward and both these rotors are connected to one another through some sort of shaft or base or something, then the desired angular momentum desired top, and the bottom angular momentum desired bottom will actually cancel each other out, because if we look at it in components, LDT, and then LTB, when they both pitch forward, what happens is that there's a component in the upward direction of LDT, component in the downward direction of LDB, component, so those cancel out. And then we have a component in the leftward direction of LDT and rightward direction of LDB, so those cancel out. So what this informs us is that we will not have to worry about any form of gyroscopic precession or that 90-degree shift because the angular momentum of each blade cancels each other out. Right? And we can prove this. Change in angular momentum is equal to torque. The torque is what was necessary in order for the 90-degree phase lag of the conventional helicopter. However, here, our initial angular momentum, looking at this as a two-blade system, is such that, okay, angular momentum initially, we have angular momentum the top blade up, angular momentum of bottom blade down. So we start off with 0, and final angular momentum is also 0 because they're cancelled. So we essentially have 0 minus 0 equals torque. Final 0, initial 0 equals torque. Therefore, 0 equals 0, torque equals 0. So that's definitely one great thing about contra-rotating blades. You do not have to worry about torque, and you do not have to worry about the phase lag that conventional helicopters experience. So that's been Anonymous, and thank you for watching.